Okay, so in this section, we want to conclude our study of graph theory by discussing what are called Eulerian and Hamiltonian graphs. And we're going to begin this section with a very famous graph theory problem called the Seven Bridges of Königsberg problem. The origin of this problem is very interesting. So Leonhard Euler, the famous mathematician, was in Königsberg, and that's just a major city in what was at the time Prussia. So this city was traversed by a river, and there was an island in the middle of this river, and then bridges that would connect it to the mainland on opposite sides of the river. And what Euler was interested in is it possible to start at any vertex, and in this instance, the vertex A, B, C, and D are just land masses, okay? And traverse every edge only once and return to the starting vertex, meaning could I possibly start at one of these vertices, which would just be on land, and then each of these edges right here in my graph was an actual bridge, and this is why this is called the Seven Bridges of Königsberg problem. If we take a look for this right here, the size of this vertex set is 4. A, B, C, and D are what I'm calling my vertices. And the size of the edge set, you guessed it, is 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. There we have the 7 bridges. And so the idea of the problem is it possible to start at a vertex and travel and traverse every single edge once and only once and return back to the vertex? Well, that was a fail on that instance right there, because I didn't hit or traverse these two edges right there. So that's the motivation of this very interesting graph theory question. Okay, can I traverse every edge only once and return to the starting vertex? So let's recall the following definition. The degree of a vertex is the number of edges incident on V, and note the degree of a loop is 2. So a couple of definitions. Let G be a graph. A trail of G that contains each edge of G is called an Eulerian trail. Let G be a graph. A cycle or circuit that contains each edge of G is called an Eulerian cycle or Eulerian circuit. If G has an Eulerian circuit, then it is called an Eulerian graph. Now, this next theorem is super important to help us determine whether a graph is Eulerian or not. So a connected graph G is Eulerian if and only if, okay, so this is this whole biconditional idea. This is why we study logic and biconditional statements in previous sections. So we have the whole P if and only if Q, so the hypothesis and the conclusion right here. So a connected graph is Eulerian if and only if each vertex in G has even degree. And the converse is also true. If each vertex in G has an even degree, then the graph is Eulerian. That's what this biconditional if and only if means. So we're going to use this theorem to check and see if graphs are Eulerian or not. So use the previous theorem to verify that the seven bridges of Königsberg problem, or graph, is not Eulerian. So if I were to draw a very quick sketch of this graph yet again, like so. And if I label the vertices V1, V2, V3, V4. Okay, so let's sketch out a very basic proof. Okay, let's take a look at the degree of each of these vertices. So for vertex 1, the degree of the vertex, if we return to the definition, okay, is the number of edges incident on V. That's just a fancy way of saying, okay, how many edges are connected to V1? So that's 1, 2, and 3. So the degree of V1 is 3. What about the degree of V2? That's 1, 2, 3, 4, 5. That's 5. The degree of V3, that's 1, 2, 3. And the degree of V4 is also 3. Now, what are we going to simply conclude? Since every vertex in G does not have even degree, then G is not Eulerian. Thus, we cannot start at a vertex, use each edge only once, and return to the initial vertex. So we just proved that this graph that models the seven bridges in Königsberg is not Eulerian. So there's no way to start at any of these vertices and traverse every bridge or every edge. There's 7 of them, okay? Only once and return to the same starting point. Okay, so let us continue our study with Eulerian graphs. And we'll skip around on this next example because it has several parts on it. But for each graph, verify that the graph is Eulerian using the previous theorem and find an Eulerian circuit. Okay, so the complete graph K5. Okay, so if I were to sketch K5 quickly, and so let's first verify that this graph is in fact Eulerian. And so the way that I can do that is find the degree of each vertex. So the degree of V1 is 1, 2, 3, 4. V2, 1, 2, 3, 4. Hopefully we see that this is going to be the same, equals the degree of V2. This is going to equal the degree of V5. It's 4. The degree of each vertex is 4, so I would simply say since the degree of each V sub I in the graph G is even, we can conclude that the graph G, in this case K5, is Eulerian. So that simply means that there's an Eulerian circuit. So I'm going to attempt to draw this graph, okay, and use each edge once and only once, starting and stopping at the same point. So let me resketch this graph. Notice what I can do is I can traverse the perimeter like we just did, and now I can do the inner star more or less, like so, and there we have it. So to draw it in a directed fashion, I could go like so, here, and then here, and then here, and then all the way back to where we started. Okay, what about the complete bipartite graph K24? Okay, so what would K24 look like? So I'm going to draw a rough sketch of K24. So K24, 2 vertices in the U set and 4 in the V set. So I might call this U1, U2, V1, V2, V3, V4. And what does the complete bipartite graph look like? So this U is connected to everyone in the V set, and same for this one right here. Okay, so let's look at the degree of each vertex first, okay? The degree of each U sub I, that's 1, 2, 3, 4, 1, 2, 3, 4, is 4. So if you're in this U set, these 2 vertices over here, their degree is 4. And the degree of each V sub I, 1, 2, each of these have degree 2, is 2. Since each vertex in K24 has even degree, the graph is Eulerian. So what that means then is that I can sketch this graph. I can start at one point and use each edge once and only once and end up at my starting point. So let's see, can I possibly redraw this carefully? To where I use each edge once and only once. Okay, so let's go from, these are the U's and these are the V's. So let's go U1 to V1 and then V1 to U2. We'll go U2 to V2. We'll go V2 back to U1. Notice I can return to the same vertex over here, U1. I just can't reuse the same edge. We'll come here to V3. We'll go to U2. We'll come to V4. And then I'll go all the way back. And so as you can see, we used each edge once and only once. So this graph is Eulerian. Okay, let us take a look at a couple more. So let's take a look at the two Sierpinski graphs. So these 4 triangles here, more or less. So let's take a look. The degree, I'll just call this V1, V2, V3, V4, V5, and V6. So the degree of V1 is equal to the degree of V4 is equal to the degree of V6, 6. So all of these guys have degree 2, and the degree of V2 is equal to the degree of V3 is equal to the degree of V5. So 2, 3, and 5. So that's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so each vertex has even degree. So the graph G is Eulerian. So what does that mean? That means that I can start at a given vertex, and I can use each edge once and only once and return to the same vertex. So let's just say that I start right here, and let's see, can I trace over this graph? Sure. Let's come here. And the path, this Eulerian circuit may not be unique, meaning there may be multiple circuits that one could find. Okay, but let's come here. We'll go here. Yeah, let's just go here. And now we'll take a loop on the inside of this triangle like so. Come back down like so. And now we'll go across these two edges back to where we started. So sure, I guess if I want to try and draw it with some directed arrows, I could. So we'll come this way, take a turn, travel the inner triangle, like so, and then the outside as well. So there we have it. Okay, let's skip the octahedral graph for the sake of time. And we'll skip the fish graph too. There are some fractals. You can read about that. It's pretty cool. Okay, let's slide down here and briefly discuss the handshaking theorem. And I think we might have briefly touched on the handshaking theorem off and on throughout the course, but here we see it again. If G is a graph with M edges and vertices V1 to Vn, then the sum of the degrees of all the vertices is equal twice times the number of edges. It is equal to double the edge set. So the sum of the degrees of all vertices is twice the number of edges, and hence always even. That's important, okay? 2 times m, okay, is always going to be an even number, okay? So, I'll let you read the proof. It's not that important, okay? But here's a corollary to this handshaking theorem, okay? In any graph, the number of vertices with odd degree is even, meaning there will always be an even number of vertices with odd degree. And you can check the 7 Bridges of Königsberg graph, okay? So let's use this handshaking theorem, okay, to answer a couple questions. So use the handshaking theorem to determine how many edges are there in a graph with 10 vertices of degree 6. Okay, so I have in essence V1, V2, all the way out to V10, and the degree of each V sub I, okay, is 6. So if I were to find the sum of the degrees of each V sub I, well, if I have 10 vertices, each of them with degree 6, that is 10 times 6, that is 60. Now, this 60 is equal to twice the edge set, where m is the number of edges. So if 60 equals 2m, then m equals, in this case, 30. So there are 30 edges in this said graph. Okay, let's do one more. So each justice on the Supreme Court shakes the hand of every other justice at the end of a judicial session. How many total handshakes occur? Now, I guess I would say that this question is slightly loaded or biased. We first have to know how many justices are on the Supreme Court. So we'll just say, note, there are 9 justices on the court. Okay? At the end of the session, everybody shakes everybody other's hand. Okay? In essence, what this would be, if I wanted to draw it, it would be K9. In essence, I would have 9 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And each justice is going to shake the hand of every other justice. If we see what's happening as we construct this, like so. And it's going to get big really quickly, so I'm not going to draw it all out. Okay? But I can simply use the handshaking theorem. Okay? So the sum of the degrees in this graph right here, well, let's see how this would be out. There are 9 vertices, 9 judges, and each person shakes 8 hands, okay? It'd be kind of awkward to shake one's own hand. So if I'm one of the 9 justices, then I would shake 8 other hands. So that would be 9 times 8, so that's 72, and that's going to equal twice the edge set, this 2 times m. So in this case, m would equal 36 handshakes. In essence, K sub 9 has 36 edges. That's what this is more or less saying. Okay, let us pivot. And instead of talking about Eulerian graphs, let's introduce a new definition of something called a Hamiltonian graph. So, a path in a graph that contains each vertex in G exactly once is called a Hamiltonian path. A cycle or circuit in a graph that contains each vertex in G exactly once is called a Hamiltonian cycle or Hamiltonian circuit. A graph that has a Hamiltonian cycle is called a Hamiltonian graph. Okay, so how is this similar? How is this different from Eulerian graphs? So Eulerian graphs had Eulerian circuits or cycles. In that, I could not repeat the same edge. In an Eulerian graph, I cannot repeat the same edge. In a Hamiltonian graph, I cannot repeat the same vertex. So once I cross a vertex, I cannot return to him. Okay, so for each graph, verify its Hamiltonian by finding a Hamiltonian cycle. Okay, so C sub n, so the cycle graph. Well, this should be fairly straightforward. This right here is C3. Notice I drew this graph. I started here at V1, and I drew this graph, and I visited each vertex exactly once. What about C4? That's not hard. 1, 2, 3, 4. There we have it. Each vertex got visited once and only once. Okay. The complete graph, Kn, for n bigger than or equal to 3, is also Hamiltonian. Let's take a look. K3. Well, K3 is the same thing as C3. There we have it. What about K4? So I'm going to draw it first. This is K4. Remember that K4 is planar, and so this is the planar representation of it. So I want to attempt to draw this graph, and it's important when assessing a graph's Hamiltonian capability, I don't have to use every edge. I only have to visit each vertex once and only once. So let's start here. I'll just call this V1, and I could go here, then here, then here, then here. And notice, I completed a circuit, and I visited each vertex once and only once. Okay. Let's do a couple more. For each graph below, determine if the graph is Eulerian, Hamiltonian, neither or both. Okay, this sounds interesting. Okay, and if it is, find the given cycle. Okay, so let's take a look at this one right here. I'll just call this graph A, and I'll call this one over here graph B. Okay, I can go ahead and tell you that A is not Eulerian. How do I know that? 1, 2, 3. There's a vertex of odd degree. Anytime there are vertices of odd degree, not Eulerian. Okay, what about Hamiltonian? Can I draw graph A, or let me rephrase. Can I construct a cycle in graph A and visit each vertex once and only once? Sure, let's see. I'm going to start here at V1, and let's see this path. We'll just come all the way, like so. I simply need to visit every vertex only once, and then end back to where I started. Sure enough. So there is a Hamiltonian cycle. So this first graph is Hamiltonian. I could spell. it is Hamiltonian. Okay. What about over here, graph B on the right? Well, I can go ahead and tell you that it is not Eulerian. How do I know it's not Eulerian? There are several vertices right here. One, two. These vertices right here have odd degree. So it is not Eulerian. Okay, is it Hamiltonian? Can I draw this graph, or can I find a cycle in this graph, and visit each vertex once and only once? Let's check. Let's come here. There we have it. So there is a Hamiltonian cycle in this graph, okay? Two. This graph right here is not Eulerian. Oh, I forgot to say that this one was Hamiltonian. This is not Eulerian because these guys right here have odd degree. So remember, for it to be Eulerian, every single vertex has to have even degree. Okay. So this guy is not Eulerian. My claim, it is also not Hamiltonian. How can we conclude that? Well, let's take a look. Can I find a Hamiltonian cycle in this? Okay, so let's just say I start in the center. I come here, pick a path. I have to visit every vertex. If I go back to the center, then I will not have visited this vertex here at the bottom. So come down here. But then that's going to run into a problem because if I travel this way right here, I've already visited this, this vertex. So this graph is not Hamiltonian. So, there's that one. Let's look at one that's both, because I know you're probably curious, okay, what would one that looks like that is both? Okay, so let's take a look at this graph right here, number 4. So let's look at the degree of each vertex. The degree of each v sub I, that's 2, 4, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. The degree of each v sub I is even, so this graph G is Eulerian. Okay, let's see, is this Hamiltonian? Can I find a Hamiltonian cycle in this graph? So I'm going to start here at A. So yeah, we can find one pretty easily. Let's just go A to B, and we'll come here, and then we'll come here, and then we'll come here, then we'll go into the middle to go to D, and then we'll come down to C, and then we'll come back up to A. And there we have it. So this graph is Hamiltonian. Okay, let's slide and take a look at a theorem to conclude this section. let G, this is a basic test, because the previous examples we were just trying to kind of brute force hunt for this Hamiltonian cycle, but here's a theorem that we can use to help us out. Let G be a simple graph on bigger than or equal to 3 vertices if for every pair of non-adjacent vertices, U and V, if we have the degree of U plus the degree of V is greater than or equal to N, then G is Hamiltonian. Okay, so let's use this theorem to take a look at one or two of these examples. So use the previous theorem to show that G is Hamiltonian. Okay, so for this graph, let's first look at the number of vertices. 1, 2, 3, 4, 5, 6. Okay, so this is what I'm calling N. Okay, now let's look at the degree of each vertice. That's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So the degree of each vertex is 3. Okay, so for every pair of non-adjacent vertices, the degree of U plus the degree of V is greater than or equal to N. That is, 3 plus 3 is bigger than or equal to 6. So G is Hamiltonian. What do I mean by non-adjacent? I'll just call this V1, V2, V3, V4, V5, V6. What do I mean by non-adjacent? The degrees of all of these are 3. V1 is adjacent to V2, V6, and V4, but 3 is vertex 1 is not adjacent to vertex 5 or 3. The idea is for every pair of non-adjacent vertices, though, the degree of U plus the degree of V is bigger than or equal to N. In this case is 6. So this graph is Hamiltonian. And I could find a Hamiltonian cycle in it without much difficulty. Let's see. Can we find a Hamiltonian cycle? Sure. Let's just travel here, travel down. Let's go into the middle. Let's go down. And sure enough, I made it back to where I started. I visited each vertex once and only once. So, nice little trick, nice little theorem right there that I can use for graphs to see if they're Hamiltonian or not. So, the idea in this section is to just use a couple of theorems to determine, is a graph Eulerian, is it Hamiltonian? Okay. I don't have time. We'll just skip the Peterson graph. But yeah, there's lots of cool things that you can do with graph theory, with Hamiltonian paths and cycles. There's the Knight's Tour problem that you might have to program in a computer science class. Okay, and we've got a nice little graph. This is a 4x4 chessboard. And what this shows is the number of squares that a knight could move to based upon where he is, for those of you who are familiar with how a knight moves in chess. And then I can expand that to an 8x8 chessboard. And so there's a graph of, I guess, what you would call a knight's scope when playing chess. And for those of you who are vaguely familiar with the game of chess, okay, a knight is most active when it's in the center of the board. Why is that? Well, the degree, okay, the degree of these vertices here, okay, are 8, as opposed to on the perimeter 2, 3, maybe 4. And so a knight's more active when it's in the center of the board. So yeah, cool stuff that you can do with Hamiltonian graphs and cycles. And then, sure enough, there's risk. You can view risk. A nice little board game right here. Maybe you're familiar with it. I can draw the risk map as a graph. Okay. So yeah, just very interesting. So that's going to conclude our lesson on Eulerian and Hamiltonian graphs.